basically, in this presentation, I'm going to show you what happens when you take an astronaut, which is basically a knuckle-dragging Neanderthal, and put him in an environment of which he knows nothing about and has to learn to make sense of what's around him. So, analogs are environments where we try to simulate what would happen if we are actually in space, if we are on a low gravity environment, or if you're trying to do exploration on a surface of some planetary environment. Why are analogs important? Well, they're important for several reasons. There are things that we can train for in a lab, we can train for in a simulated environment, in a mock-up, but there are things for which we cannot train unless we are actually immersed in that environment. And that's what analogs are for. We have several different kind of analogs right now operating in the different space agencies. NASA has NEEMO, NASA Extreme Environment Mission Operations. It's underwater. And then we can simulate, or actually we can experience some of the effects of being completely isolated in a very stressful environment. And we can actually simulate low G, low gravity. We can simulate 0 G, we can simulate partial gravity. And we can test all kinds of things underwater. At ESA, we came out with other concept. We know that most planets or most planetary environments around us have underground structures, be them caves or tubes, and we will see a little bit of a difference. So one day when we put our feet again on the moon or for the first time on Mars and we want to explore these environments, how are we going to do it? I mean, we see movies on Mars where we have the astronauts in their spacesuit and they're walking around Mars and they actually go into caves and they're just walking around the caves. However, that is not realistic. It's Hollywood, and that's why it's Hollywood. When we put the astronauts actually in that environment, we see that there are things that we need to take into consideration, and that's why we have caves. So without much ado, let's start. So squeezing through. So obviously, not obviously, but the most important part of the experiences that we do in the analogs are not only, but most importantly, are concerned with extravehicular activities, meaning on-the-ground explorations. So that's why I have this picture of an astronaut coming out. We would have to be doing these activities in the future wearing a spacesuit. Now, EMU is a very, very, very cumbersome, incredibly cumbersome spacesuit. It's heavy, it's massive, it's incredibly rigid and uncomfortable, so it's not an exploration suit. It will be an evolution of the spacesuit. So you have to imagine when we go to Mars or to the moon, it's going to be a different spacesuit, but the activities that I will show you will have to be done in a spacesuit of sorts. So squeezing through, or through a squeeze. So in this picture, you see me very happy. I'm totally pretending. But what you see me in an environment that is very, very unique. It's a very tight environment where you actually have to learn how to go through a squeeze. And it may seem simple in a way as a concept, but it's not. As a matter of fact, first of all, you learn that you can squeeze through spaces that you didn't think you could. You have to take into consideration dimensions. You have to take into consideration your own body, but also in the future a spacesuit. You have to figure out whether you can build a spacesuit that is sturdy enough to go through a squeeze or not, and how this will limit your exploration. But most of all, you have to learn to be uncomfortable. So astronauts that will do exploration on planets, on Mars or on the moon, they will understand that they will find moments where they will be very uncomfortable. and they have to be comfortable with being uncomfortable. You can go from a squeeze to incredibly vast spaces. And it's surprising to imagine that an environment like this, these are people, right here. These are people. And this is how vast the environment is. This is inside the mountain in Sardinia. So we're just not used to think that there are incredibly vast spaces underground. And if we are surprised at finding something so big underground, on Earth, we have to imagine that on a partial gravity body, it would be these spaces would be even bigger. And in a way, this poses other questions. If there are such vast spaces on Mars, deep underground, protected from radiation, protected from the cold of the vacuum or the thin atmosphere of Mars, is there stuff up there or down there that we don't know about? I would like to think that it's probably so. Imagine these on Mars, they would be 10 times bigger. 10 times bigger both in depth and in width. So just imagine what could be found down there. And that's why we believe, as a space agency, that underground exploration is very valuable. And training astronauts how to move in very complex environment, like an underground space, is invaluable. Caves specifically, as a training value, our instructors train us how to move underground, how to understand the underground, the complexity, to understand the geometry of an underground, the fact that underground geometry is three-dimensional, for example. We think of caves as something that stretches out, but because of the complexity of the formations, it actually stretches out in different directions, three-dimensionally. So unless you have experienced that, it's hard to comprehend that. So there is that value of training of how to move, how to explore, how to look around. But also there is actual scientific value where we collect samples. We are trained by our instructors to collect samples that are later analyzed by the scientist. I don't have to be a scientist to collect a sample, but I have to be trained on how to collect the sample without contaminating it. Now, contamination is going to be a huge factor when we go back to the moon or to Mars, because if we are looking for life and we bring our own life out there, then we are beating the purpose. So learning how to be in an environment that you cannot contaminate and still interact with this environment is something that needs to be learned. Luckily, on Earth, we do have life. Life is incredibly resilient. And so even in the most inhospitable places and places where you wouldn't imagine life to exist, we do find life. So underground, part of our job was to collect biosamples. There are tiny creatures that have adapted to live in places with no light whatsoever and almost no food available. So these creatures are tiny, they're hard to find. You have to understand how to look for them, how to recognize them. And basically in every expedition so far, we have found new species. So not only we are learning how to look for life, how to identify it, but we're also doing real science, because then when we collect these samples and we take them out, scientists have been able to identify them as new species. Funny things about this environment, it proves evolution if you needed more proof. Apparently, sometimes in the US it does. But if you need more proof of evolution, it proves it in a very unconventional way. These animals have no eyes, because if you have no light, eyes are useless. It takes energy to form eyes or to have these organs, so evolution gets rid of it. So no ice, but they have other sensors. They have antennas, they have temperature sensors to use what they can in order to orient themselves and find food. Also, color makes no sense when you have no light. And so most of these animals are either white or semi-transparent because they don't want to waste any of the little energy that they can find to create colors. But anyway, the main point is learning that how to find life, where to look for life, what life can look like, and how to collect it again, either without damaging it or, again, without contaminating it and without interacting with it in a safe way. A very important part of exploration is understanding that astronauts will have to make independent choices. We have forgotten about that. We are so used to being on the space station where everything is controlled on the ground, by the ground. We just, most of the time, but when I say most, it's the almost totality of the time, we just execute a plan. But when you do exploration, actual exploration, as a crew, you're going to make choices. And these choices will affect how the rest of the exploration is going to go. Which it could mean that it goes into the wrong direction, or it could mean that it goes into the right direction. But astronauts need to understand that, astronauts or explorers in general. So we are given the tools to make those choices. We are given the understanding of how to make choices. But then in the end, it's going to be our responsibility to make the choice. Learning to come out with the responsibility, first of all. And secondly, learning as a crew to agree on what those choices are going to be. Again, it's something that needs to be taught. It doesn't come naturally. So you have different roles, but then in the end, in a very stressful environment like being underground for 5 to 6 days, these choices become harder and harder, and the ramifications of it becomes also more and more complex. As I was saying, caves can be incredibly complex environment. And if you think that moving around using rappelling or going down using different techniques is easy, well, I tend to think that everything is easy if you put your mind to it, but it's a very physical environment. And it reminds me that EVAs are very physical. Even though in space we can be weightless or in partial gravity, because of the constraints of the spacesuit right now, doing an EVA, an extravehicular activity, is incredibly physical, very, very physical. While being underground at a constant temperature and very high humidity, with a suit, that is not as uncomfortable as a spacesuit, but it is a suit of sorts that you need to use in order to protect yourself. And moving around in an environment that is very, very alien to you is also very physical, and this physicality needs to be understood. We have to understand that the astronauts that get to Mars, they will have to be in strong physical conditions, even in a partial gravity, in order to be able to do a traverse, to move around, to climb, to descend, to come back in order to be safe. The cave environment is incredibly complex, I would say. Moving in a three-dimensional space where there is only one way to go, one direction, is, again, something that needs to be learned. Also, we are so used to having tools that help us navigate that we take it for granted. You know, most of you, probably the young ones, don't remember what it means like to stop and ask for direction looking at a map. But, you know, if you have a cell phone, you probably have used Google Maps, or whatever. But underground, you cannot even use a compass, as a matter of fact. You go deep enough, magnetic field is not strong enough to guide you and Mars doesn't have a magnetic field, as a matter of fact. So if you could use the star field on the surface in order to navigate, underground on Mars, you wouldn't have any instrumentation. So imagine how complex it is in a dark environment with no navigation capability to move around without getting lost. Does it?
Everything is north anyway.
Everything is north?
If you're going to South Pole, everything is north.
Yeah, absolutely. So either way, this is a skill that needs to be learned. How to navigate in an environment where that is not hasn't been mapped, and that doesn't offer you any tool, any way to guide yourself. Again, even though caves as a program is actually a training program for astronauts to learn all these skills that I've been talking about, one of the most fun part about it is that it's actually real exploration. And for us, this was a very momentous day when we popped out from a squeeze. We have been exploring a very interesting part of the cave with very cool formations. We had stalagmites and stalactites, very big and interesting. We had an area with huge boulders, perfectly spherical. And to this day, I don't know how they formed. I don't know if Cesco, who is the expert here, has a better idea. He has probably a better understanding. But we called it a ballroom. But it was incredibly fascinating. But advancing away from this area, we just popped through a squeeze and we found this incredibly vast room with this wall, sheer wall. And what you're looking here, we are sitting on the remaining of what collapsed from this wall. And we thought that we were the first ones there. Well, as astronauts, our exploration had gone further away than the previous one. So for us, we were the first ones there, and we actually posed in front of our biggest discovery, this enormous room with this very, very sheer wall with a collapse. Isolation, not to be taken lightly. Being isolated adds complexity to an already complex environment. I chose this picture because, as a matter of fact, when we arrived into the cave, when we descended initially, we set up a base camp. And even though we were isolated, we still had a lot of connection to the outside. Our trainers and our logistic advance had placed a phone cable through the whole cave, a couple of kilometers, I believe. A couple of kilometers of a phone line so that we could talk to the outside and have a contact with them. So even though we were isolated, meaning we still were a couple of kilometers underground, we had our tents, we had our food that our Sherpas had brought inside. So a lot of logistics had been taken into place. It would be the equivalent of descending on the surface of a planet and having there a logistic camp. Kind of like you've seen in the movie The Martian, probably, if you've seen it. Now, in this picture, you have an advanced camp. We abandoned our original base camp. We moved through without being able to string a phone cable and only carrying the minimum that we could, the minimum amount of food, of logistics that we could carry with us in order to advance further away. In that moment, for those 48 hours, we were really isolated. So the risks increases exponentially. Something happens, now you have to take care of it on your own. If again, your choices now are going to matter a lot more because you're not going back to the base camp and saying, okay, we went this way, it was wrong, let's go the other way. Now you picked a point that is going to be your new base camp further away, and now your every choice is going to make a bigger difference. Again, those ramifications. And you have to be conscious of that. Again, this is not a skill that you can tell people about. You have to feel, you have to experience, you have to learn how to cooperate with that. And also understanding and being comfortable with this feeling of isolation is going to be absolutely important for those that will be on the surface of the planet. That's why we call it an analog. It is on Earth, but it's like being somewhere else. Another part of caves that is very consistent with what we do as astronauts. As the astronaut corps, we like to say that what we do in space is science, technology and exploration. So obviously, the science and the exploration, we already saw parts of it. But I like to say that testing a new technology is just as important. I think that the exploration part is what really drives us. But in order to enhance the exploration, to make it possible in the future, we have to test new stuff. In here, you see Misha Misurkin, Sasha Misurkin, one of our crew members, using a piece of equipment that basically is a radio that allows the communication to go through the rocks. And this is something that we tested with ambivalent results. Sometimes it worked really well, sometimes it didn't work so well. But it is new technology, and imagine how valuable this would be if we make this technology work really well, reliably. Then you can imagine being on the moon in a lava tube and using this technology 10 years from now, or on Mars 20 years from now. But in order for that technology to be available and ready, then it has to be tested now, and retested, and redeveloped and retested. So we need an environment that lets us do that operationally. This is such an environment, and being able to be part of that as operators is priceless. You seriously cannot put a price tag on that. And finally, understanding an alien world. This is, I'm not 100% sure if this is before going in or before coming out. This is only a couple of hundred meters into the cave. It's the witch's head, right? Yeah, this is pretty clean, and we're all smiling. Also, I think I'm freshly shaven, so this is right before going inside. And we're all happy, we're smiling, we are excited to go inside this alien world because we already spent about a week training into similar environments. So there was an incremental approach to this. We spent half days into a cave understanding how to move, how to analyze, how to interact with the environment. And now we are going into this alien world. We feel confident. We're all smiling. We're excited. Well, we were so confident. The confidence comes from understanding. This is so important to understand. You cannot go to a place unprepared. That's how all horror movies are made. You know, there's a bunch of kids that decide to spend the weekend in the mountains, and they all die. Because there's a monster, because they all fall into the crevices, because they're not prepared. They think it's possible, they think it's easy, and it's not. Going to the moon is not easy. Exploring the moon is harder. Going to Mars is even harder. Exploring Mars, it's exponentially harder. But in order to go there with a smile on your face and not die, we have to need an incremental approach. And it starts right here on Earth, understanding the complexities and all those things that I already told you. So I hope that in the future we can go to Mars with a smile on our face, ready to go inside a cave, exploring and understanding such a complex environment. That understanding starts in caves. Now, a couple of words about Pangaea. Pangaea was a much simpler project, both logistically and in terms of execution. But because it's such a much simpler project, the payback, what it gives you back, is actually as a higher delta. So, Little Green Man, this is the crew of this test run of Pangaea. You have Pedro, you have Matthias, myself, and we are standing on Mars, or what it looks like Mars. So Pangaea was in two parts. The first part was purely mostly theoretical. We just tried to learn about geology, as a matter of fact, what field geology is all about. So first you talk to the scientist, you are given explanations of what's going to happen. We had some practical exercises, but then it all came together in Lanzarote, which is where we are. By the way, if you have never been to Lanzarote, you should really go. It's awesome. So Lanzarote is amazing because it really looks like Mars. And I've never been to Mars, but I've seen the movies, so So Lanzarote offers in a very small, in a relatively small island, definitely small. I come from Sicily, which is a very big island. So Lanzarote is such a small island, but it offers a lot of different environments. It's such a geologically active place that you find all sorts of interesting locations where you can do field geology. This is actually one of the last traverses that we did, but it really gives you a sense of how diverse the Earth can be. And to me, it really looked like I was walking on Mars. And what do we learn from walking on Mars? Well, if you put, have you guys ever seen the series From the Earth to the Moon that was produced by Tom Hanks? No, you really should. There is one episode.
By the way, we have the DVD in ESA, so if anybody wants, I have it.
There you go. They're not mine because somebody stole mine and never gave them back.
I have it.
Anyway, one of the episodes on this series is about geology science on the moon. The first missions, 2 famous astronauts landed on the moon, or mooned on the moon, I don't know how you say it, and then walked around, demonstrated it was possible to get that. On the second mission, they demonstrated it was possible to pick a spot and land in that spot, and so on. And then we started thinking, okay, but what are we doing on the moon? We need to make it worthwhile in terms of science. Now, if we keep collecting rocks without knowing what we're collecting, we might as well go in a Japanese garden and grab whatever we find there. We need to have an understanding of what we're collecting. So what is easiest? To take a pilot and teach him, again, a knuckle-dragging Neanderthal, because that's what we are. Is it easier to take this knuckle-dragging Neanderthal and teach him how to science the hell out of it, or to teach a scientist how to be a pilot? Well, it turns out you can do both. But either way, there's going to be training required. And this is part of it. Understanding morphology means that morphology on Earth tells you a story, a very important story. It tells you the story of a planet, of a comet. It tells you the story of a planetary body. That story has a language. So when we are 5 years and 6 years old, we learn how to read, and then we are able to take a book and learn the story that's inside the book. Now, in order to learn how to read a story like this one, like this image that we're looking at, it takes years. Now, to imagine that you take a pilot and you teach him exactly how to read this story and understanding it, it would be complicated because it would take infinite amount of time to teach an astronaut to do everything. So what can we do? We can tell the astronaut how to read, maybe without understanding, but at least he can read. And if he can say the words, then somebody else can pick up those words and understand what's being said. You see the difference? If I learn how to read Cyrillic, I can open the book in Cyrillic and read it perfectly. And I don't understand anything that's written in there. But somebody can hear me and understand what's the story. That's what we're trying to do. How long does it take to teach an astronaut how to sit in the middle of this crater, look around, and make a description of what he's seeing, so accurate and relevant in terms of words, in terms of technicality of it, that the people on the ground can have a very good understanding of what they're seeing. So that's the part, the experiment and the training that we're getting in Pangaea. And there it is, learning a new language. Matthias is pointing at the sky. I took this picture because it's kind of emblematic. I don't remember what he's pointing at, but probably pointing at Pedro. You fool! Yeah, but we had 3 very different people. We had a pilot, an engineer, and a pilot and 2 engineers, well, Matthias is in between engineering and scientist, learning how to read those elements. And it turns out that with the right training and the right instructors, you can teach these people, very different people, how to be in an environment that's completely alien to them and use the right words to describe that environment. This is valuable experience. Now, obviously, we're not going to the Mars tomorrow. I'm probably not going to go to Mars. But to understand how to do that in a small amount of time, and how much time is it required to teach that, that is part of what Pangaea was about. Getting dirt or dirty sampling. Again, Pangaea was also about real science on the ground. We did get dirty. We did collect samples. We did look at dirt, rocks, different kinds of materials to figure out what was happening and to understand also how to sample, but mostly how to pick what to sample. Because let's say, imagine you're on the moon and everything is gray around you. How do you pick what is important to sample? And if you're on Mars and you have a 20-minute delay before you ask a question and it comes back with an answer, you're not gonna have the luxury of saying, hey, do I pick that rock or do I pick that rock? And what if you only can pick one rock? You have to have some background, some language with you, something that gives you at least the confidence to say, well, they're probably both important, but I'm going to pick this one because it's more important. We had learned, in part, how to do this during the Apollo missions, but that was 40+ years ago, almost 50. And unfortunately, even that kind of skills get lost. We don't have the same people. We don't have the same astronauts. We don't have the same instructors. So we are going to have to relearn how to teach the astronauts to pick the right rock. So while we were in Lanzarote, we also explored a different kind of cave. This is not a cave. It's a lava tube. And we just had a very long conversation with Cesco here about why it is important to explore lava tubes. Lava tubes are all over our planetary system. They are on the moon. They're huge, huge tubes protected from radiation, protected from the vacuum of space. And we don't know, at this time, we don't know what's inside the lava tubes. We don't know the environment inside those tubes. So it is something that's there. It is something that we could explore. And it's something that could be valuable even as an environment to put our habitats. Instead of building a dome of regolith, we could just go inside, put an inflatable tent inside a lava tube, and now we are already protected. And all we have to figure out is how to climb inside and outside, which we could ask the Mexicans, and they have very good ladders. So, but jokes apart, lava tubes are everywhere, and understanding that they are there, and even on Mars, much bigger, again, it's one of those things that tells us that we need to know how to explore this environment and understanding them. Am I boring you yet? Okay. So again, science, technology, exploration, technology. We like to test technology. And this piece of equipment, I believe it was one of the first field operations that we were doing. This is an instrument that utilizes infrared technology to pick up the composition of what we're looking at. Now you take the old Neanderthal and you give him a rock, and I have no idea what's in the rock, but if this piece of equipment has the correct library inside, I can point at it, shoot for a couple of seconds, and it tells me, hey, this rock is interesting, this rock is not interesting, it's the same as the one that you've been looking for. It just looks different, but it's the same composition. So, hey, why does it look different? Maybe I want to pick it up anyway because it looks different and it's the same, or it's completely different. So, real testing, real technology, new technology. And imagine if we have something like this on a rover. Now you're driving a little rover on the surface. It looks down, finds something. The scientists are not convinced, is it interesting, is it different, is it new? You just pointed it, and in a couple of seconds you have the result. It analyzes it for you, it tells you what it is, as long as you have the right library inside. Well, even if you need the right library inside, you need to build it, and in order to build it, you have to have all kinds of different materials, and so this is also part of it. And finally, spreading the word. So this is a lava bomb, by the way, and what it is, it's a huge piece of lava that fell in a blob, and then it cracked. They're not usually this big. This is really big. But spreading the word, what I'm talking about here is communication with the public. If you have a fantastic story, a fantastic experience, the best one ever, and you don't tell anybody, it never existed. So we as agencies, and I'm talking about ESA, but also NASA, JAXA, we are not really good at talking to the public. We are not. The only times that we really get some response is when we have some human interactions. And so events like this, NEEMO for NASA, Caves and Pangaea, get a huge response. We talk to the public about what we're doing, about our experience, about being underground, underwater, on the surface, and doing different things. We get a huge response. Why is that important? Because it tells people what we're doing, and it encourages them to look at what we do. And if you are a 10-year-old kid that gets inspired about becoming a geologist, a geophysicist, or an astronaut, why not? Even if 1 out of 1,000 decides to do that because of my experience on Lanzarote, then so be it. I will have done my job. So it is just as important, and the value, the communication value of this experience is absolutely not to be underestimated. It is absolutely important. 40 minutes, not bad. So have I convinced you of the importance of analogs and why is it important to train underground and understanding the language of geology? I see a couple of heads shaking, but that's good. That was the point. That was the point of this presentation. Thank you for your attention. Unless you have any other questions, we can all go have lunch.